Okay, so in this lecture, we'll be talking about the measurement techniques for piezoelectric energy harvesters. But before we start piezoelectric, how to do the measurements of piezoelectric energy harvesters, before we start talking about its measurement techniques, we'll start with very fundamentals of what is piezoelectric energy harvesters. But before that, let us understand that what is a, a energy harvester. So energy harvester, it is a very intense topic. Okay, where the ambient source of energy are harvested and which is converted into useful electrical energy. Okay, and mostly piezoelectric energy are energy harvester most basically it enables the conversion of movement and vibrations of the environment as well as the human motion, right? So with this, let us just start, and we'll start talking about very fundamental things about the piezoelectricity first, and then gradually we'll talk about the measurement techniques. But before that, we need to understand that what is a piezoelectric material. So, so okay. So let us first try to understand a little bit of basics of the uh, piezoelectric material or piezoelectric and ferroelectric material. Then we'll talk about these, right? So piezoelectric material, if you are talking about a piezoelectric material, it will undergo if you have a piezoelectric material, it undergoes a changes in the electrical polarization when mechanical stress is applied. Okay, so when mechanical stress is applied, let me change the color. Okay, so when mechanical stress is applied, okay, when you are applying mechanical stress, and then you generate electrical energy from that then it is what you call a direct piezoelectric effect, right? This effect can create, so this is what you call direct direct piezoelectric effect. Okay, and this effect can create an electrical current in the external circuit and can therefore be exploited as electromechanical generator to harvest energy. Okay. Now, when piezoelectric material also can undergo a mechanical strain if you are applying an external electric field. This is termed as, so if you are your stimulation, so basically if your stimulation is electrical, so if you are applying an electrical voltage or electrical signal, okay, and then if you so electrical voltage, let's say if you are applying voltage, okay, if you are applying a voltage, then what will happen, then you can the material can undergo a mechanical strain, so it will undergo a mechanical strain. That is what you call indirect indirect uh, piezoelectric effect, right? And in this case you generate strain, in this case you generate voltage, so mechanical stress will produce voltage where if you are applying electrical voltage, it material can be strained. Okay, this is what is indirect. So in this is what is called indirect piezoelectric effect. This is more so this indirect effect is more useful for actuator applications. It is more applicable for actuator actuator application actuator application. Okay, now why this piezoelectric effect are there in the material? For that you need to understand that it can only be seen if you have a non-centrosymmetric crystals. Okay, if you have a non-centrosymmetric crystal, then only you can see this effect in the material. In the material, you will see this kind of effect only if you have a non-centrosymmetric. If you have a non-centro non-centrosymmetric crystal. Okay, if you have a non-centrosymmetric crystal, then only you will find out this. Okay, now ferroelectrics are a subgroup of this piezoelectric material. Okay, now the ferro. Okay, so now let us just start with the ferroelectrics. Okay, so ferroelectrics. Let me just change the color. So basically, these ferroelectrics ferroelectrics are the uh, subgroup of piezoelectric material. So if you just consider that this is a large group of this is all piezoelectric, right? These are all piezo, and ferroelectric will be a subclass of this, and this is ferroelectric material, subclass of it. Okay, how do you therefore how do you characterize this ferroelectric materials? The ferroelectric materials can be characterized by a spontaneous polarization. It can be characterized by a spontaneous polarization in unstrained state. When the material is not strained, and the capability to reorient this polarization direction via an electric field. Okay, so spontaneous polarization should be there in the unstrained condition, and this polarization should be reversed or should be able to reverse on the application of the applied field. Very classic example of this ferroelectric material is barium titanate or PZT. We all know that what is PZT. PZT is lead zirconium titanate. Okay, lead zirconium titanate. These are very classic example of ferroelectric material. These are a very classic example of ferroelectric material. Very classic example of ferroelectric material. Okay. Now there are certain polymers. There are certain polymers which is also exist as a ferroelectric material. For example, PVDF. Okay. and also some of its copolymer like TRFE. These are very good ferroelectric polymers. Okay, these are very good ferroelectric polymers. They also show ferroelectric properties. And in these polymers, basically these are crystalline polymers. These crystalline polymers, uh, these are the crystalline polymers with aligned molecular chain, where the polarity is due to the alignment of the polarized covalent bonds. Okay, so it has covalent bonds, and when they are aligned, okay, if they are aligned, then the spontaneous polarization is coming into the picture. Okay, but as we can see in the case of the ceramic ferroelectric material, their application is mainly limited by temperature, which is called Curie temperature. So Curie temperature is nothing but the temperature above which you go. If you go, material will be transferred into a paraelectric phase, and if you are below this temperature, then you will be at ferroelectric temperature. So the material is ferroelectric. Okay. Similarly, in this case of polymer also, uh, in case of polymer, similar observation can be seen. So here also, in case of let's say this PVDF or this polymer, okay, this also has a TC, so above which it actually uh, has a alpha phase, which is a non-polar phase, and above TC it will be a alpha phase, and below which, or I just let me just put it in that way. Let me just, so if I say that below which it has a polar phase of the polymer, which is a beta phase, and above TC it is a paraelectric phase, which is called alpha phase, which is called alpha phase. Okay, so above TC it become a non-polar phase. So basically this is a non-polar. This is a non-polar phase, and the beta phase is a polar phase. Okay, beta phase is a polar phase. Beta phase is a polar phase. So this can also be seen in case of polymer material also, polymer or its copolymer. It has a Curie temperature. Okay. Now, while a ferroelectric material contains many individual unit cells with a corresponding electric field, so there are regions where these unit cells have equal polarization directions. These are known as domain. So, for example, if I am talking about a bulk material, okay, if I am talking about a bulk material, it can be looking like this, and it has so many of unit cell in a smaller scale. If you just consider at the this level, so it has a polarization direction, let's say in this direction, this has a polarization direction in this direction, and this direction. So together they will be a region where all they have a polarization direction. For example, in this direction, maybe in this other part of the material, the net polarization direction in this, and maybe here it is in this direction, or it may be here it is in this direction. So these are all called ferroelectric domain. These are all called ferroelectric domain. These are all ferroelectric domain. Okay, so when a ferroelectric is cooled below Tc, okay, when a ferroelectric is cooled below Tc, there is no net polarization, as the domains are effectively randomly distributed through the volume of the material. Okay, Here also you can see all these domains are randomly oriented. So once they are randomly oriented, you won't see any net polarization. So in this case, the net polarization is zero because this is randomly oriented. Okay, so for the material to exhibit piezoelectricity, okay, at certain temperature, so at any particular temperature, all this will be randomly oriented, so you won't get any net polarization in the material, though it is a ferroelectric material. Okay, though it is a ferroelectric material, though it is a piezoelectric material, at equilibrium at means at any particular temperature, thermal equilibrium, you won't see any net polarization because of the thermal agitation. Okay, because of the thermal agitation, you won't see any net polarization. So to have this, or to make this material ferroelectric or piezoelectric material useful, to, or if I can say, the for the material to exhibit piezoelectricity, the randomly oriented these dipoles or the dipole domains are need to be aligned in a common direction to achieve a net polarization. To achieve a net polarization, all this domain has to be aligned in a common direction. Okay, at any particular temperature, at any particular temperature. So this process of alignment, this process of alignment of dipoles, or you can say the this domain, okay, alignment of this domain is what we call polling process. We call polling. We call polling process. So this is an essential process in converting an inactive ferroelectric polymer into a useful electromechanically active. Basically, so polling process, what it will do, uh, this polling process is basically an electrical alignment process. Okay, this is very essential in converting an inactive ferroelectric polymer. So before polling, a material is electrically inactive. It is electrically inactive. Okay, but after the polling process, so it means after the alignment of these domains or dipole, any ferroelectric polymer. So let's say we are talking about a ferroelectric polymer. So this ferroelectric polymer will be electrically active. It will be electrically it will be electrically active. So polling process involves the polling process uh, involves the application of an electric field. So a polling process involves the application of electric field. Basically, DC electric field is applied. DC electric field, DC electric field is mainly applied, and this DC electric field applied at some elevated temperature. Why some elevated temperature? Because at elevated temperature, domains will be little softer, and it will be easier for the easier to orient those polar axes of the domain along the polar axis. Okay, so uh, what I am saying, that at elevated temperature, some DC field which is applied to orient the So the polar axis of the domains to those direction allowed by the crystal symmetry, which are nearest to that of the applied electric field. Okay, so you know that if you are talking about a unit cell, it has so many easy axes by which this material can get aligned. Okay, uh, so domain will be aligned to those axis which will be allowed by the crystal symmetry, because different crystal symmetry has different easy axis. These are called easy axis of uh, easy axis of polarization. Okay, so to further facilitate the Pauling process, ferroelectric polymers often require a mechanical stretching, because mechanical stretching will enhance the alignment of the molecular chain, and that maybe we can discuss later. Now before we talk about that, let us just see how this polling process is done. So if you have a, let's say if you have a cylinder kind of material, if you have a cylinder kind of material, so let's say I have this kind of uh, cylinder kind of, okay, and let's say this is the domains I have. So this is plus, this is minus. So let me just put arrows to understand it. Let's say this is plus, minus, and let's say plus, minus, plus, minus, and so on. Now if you apply an electric field, let's say you are applying a electric field, so you have to put an electrode over this surface, or the whole surface you can do the electroding. Okay, the whole surface can be electroded. Okay, so this surface and the other surface. So if you just apply an electric field here, but this is a DC electric field. Okay, so you are applying a DC, let's say DC electric field you are applying. So what will happen that all this, if so this is positive, this is negative, so what will happen, all this how it will look like, now it will be looking like this. So now it will be looking like this. Here all the dipoles will get aligned. Okay, so it will be all aligned like this. It will be all aligned like this. This is plus, minus, plus, minus, and this terminal you have taken as positive, and this electrode you have add. So this is positive terminal, this is negative terminal, so they will be aligned like this way. Okay, if you have sufficient number of this thing. Okay, so it means now if you, and this is doing, if you are doing at certain temperature, you are doing at certain, let's say you are doing it as 150 degrees Celsius. Okay, you elevated the temperature, you are applying the DC field for a sufficiently long time to let them align. Okay, so this electric DC field you have applied for a sufficiently long time at certain temperature, then what you will do, you gradually decrease the temperature. So now what you do, you come to the room temperature keeping this field on. Okay, and then after, when you remove the electric field, so there is a chance that they will get at room temperature. So when you are coming back to room temperature with the uh, field on, now if you switch off the DC field, now they will be freezed, actually they will be this will be freeze. These dipoles will be freezed. So maybe there will be little randomization of this field, but not that much, which was earlier in this case. So here maybe you get a little bit of distorted this kind of field, but mostly they will be uh, aligned. Mostly they will, all these dipoles will be mostly aligned. Okay, little bit distortion will be there, but mostly it will be. So this is now a piezoelectric material. So this was the net polarization. Here the net polarization was 0 here. Here you have a non-zero value of the polarization. Here polarization is non-zero. Okay, and this is you can call as a piezoelectric material. That is what you call a piezoelectric material. So this polling process is to be done for all the material. All the material, I mean, it can be done for, it should be done for uh, bulk as well as the polymer also. Okay.